Remember how we noted a couple of things down on our to-do list to check for later? We said that we check for a potential problem in our regression, and the problem that we were concerned about was called multicollinearity. The reason was that we had some high correlations between our features, so multicollinearity was something that we wanted to test formally. Now, put simply, multicollinearity is when two or more predictor variables in a regression are highly related to one another. In that case, they do not provide unique or independent information to the model. And the consequences of multicollinearity are as follows. There is a loss of reliability in the estimates of the effects for the individual features, in particular the features that are affected. In other words, there is a high variability in the coefficient estimates for small changes in the model. For example, adding or removing a feature can have dramatic effects. The estimates of our theta values in our model become unstable and can even switch signs from positive to negative and vice versa. The third effect of the problem is that the findings are strange, or misleading, or don't make sense. These are the main symptoms of the multicollinearity problem. Now, given these symptoms, we can definitely say that on the third one, our regression definitely passed, because we did a sense check on the signs of our coefficients, and we found that the coefficients definitely had the right signs. They made sense from a logical perspective. Like more rooms increase the property prices and more pollution decrease the property prices, for example. But in this lesson, I'm going to show you how you can do a formal check, how you can look at a metric to tell you whether you have this problem or not. The formal check that we will do is by looking at a statistic called the variance inflation factor, or VIF. And the second thing that we will do is we will monitor if removing a feature causes a dramatic change in our theta parameters, but that will wait until the next lesson. Now let's go back to Jupyter Notebook and add a new section heading. This section heading is going to be called Testing for Multicollinearity. So testing for multicollinearity. And to test for multicollinearity, we said we're going to be using a statistic called the variance inflation factor. So let me quickly explain how the variance inflation factor does its job. Because this statistic is a measure of collinearity among the features within a multiple regression. And what it will do is it will spit out a number that quantifies the severity of multicollinearity. So in effect, we get a number similar to how we get a number with the p-values. And we can look at this number and compare it to a threshold. Is it above the threshold or is it below the threshold? That's how it's going to work. But before we write the Python code to actually calculate the variance inflation factors, let's add some formulas in LaTeX notation to this section heading to kind of better understand what's going on. I'm going to show you how the variance inflation factor is calculated for one of the features as an example. The first thing that will happen is that a regression will be run on that feature. Let's say we're looking at our tax features. So what will happen is that we will look to explain the tax values as a linear combination of all the other features in the data set. So you're going to get a regression that reads something like tax equals, and then some intercept, say alpha underscore 0, plus some parameter times the number of rooms, so alpha underscore 1 rm, plus some other parameter, alpha underscore 2 times the next feature, say nitrous oxide, plus, and so on, till you get to LSTAT, which will be alpha underscore curly braces 12 LSTAT. Since we have 13 features total and we're looking to explain tax, not property prices, we're left with 12 different kind of parameters in front of the other features. I've also used alphas here in my LaTeX notation so we don't get confused with the theta parameters that we used earlier. Now, this is only step 1 of calculating the variance inflation factor. Step 2 looks like this. In step 2, we get the variance inflation factor for our tax feature, so VIF underscore tax in curly braces, it's going to be equal to backslash frac curly braces 1 over curly braces parentheses 1 minus r underscore curly braces tax curly braces carré 2 closing parenthesis closing curly brace. Now let me quickly delete this backslash here, we don't need that, and hit Shift Enter to make this a little more clear. This is step 2. In step 1, a regression is being run of all the other features against tax, and in step 2, the r squared of that regression is used to calculate the variance inflation factor. So 1 divided by 1 minus the r squared of this regression up top is the variance inflation factor for the tax feature. So that r squared here is the r squared from trying to explain the tax feature in terms of all the other features in the dataset. So the point I'm trying to make is that we can calculate a variance inflation factor for all the different features, right? Just by swapping out this tax for RM, we get the variance inflation factor for RM. So in our Python code, what we're going to do is we're going to calculate 13 different variance inflation factors. Now, the stats models module actually makes this very, very easy. We're not going to have to run this like two-step calculation manually. We simply call a function. But I wanted to show you what's going on behind the scenes in the LaTeX notation nonetheless. So let's scroll to the top of our notebook and actually import this functionality. I'm going to come in here and I'm going to write from statsmodels.stats.outliers underscore influence import variance underscore inflation underscore factor. So I'm this specific function from statsmodels.stats.outliers underscore influence. Now let me hit Shift Enter on this cell. Interestingly, the deprecation warning disappeared when I did that. And I'm going to scroll back down, and now I'm actually going to call this function. Check it out. Variance underscore inflation underscore factor parentheses. And before I put any arguments between these two parentheses, I'm going to hit Shift Tab on my keyboard to bring up the quick documentation on this function. What we see here is that we need two inputs, exorg and exorg underscore index. I'm going to hit this little plus sign here, scroll down a little bit, and we can see that the first argument is an n-dimensional array. And the second argument is simply an integer. It's a whole number. And that number is basically the column of this n-dimensional array that we want to look at. All right, so we've got a data frame, x underscore including constant. And say we want to calculate the variance inflation factor for the first column in this data frame. How would we do it? Well, we can come down here and as an argument, pass in the first one, which was exorg is equal to x underscore include underscore constant, comma, and then exorg underscore index, idx, is equal to, say, 1. Why did I pick index 1 and not 0? Well, at index 0, we've got our intercept, our constant. I'm interested in our first feature, which is crime. Okay, so I'm going to hit Shift Enter on this, and you're going to see that it doesn't work. Take a look. We get a type error. Scrolling down, we see that the error description is unhashable type, slice. Why did we get this? The error message is actually fairly cryptic, unhashable type, but we do discover that it actually has to do something with data types again. Now, data types are actually usually quite hidden in Python, but occasionally, if you ignore them too much, they come and bite you when you're not careful. Remember how when we hit Shift Tab here, and we looked at what kind of argument this exarg argument should be. We found out that it was an n-dimensional array. Well, let's look at the type of x underscore including underscore constant. So writing type parentheses x underscore include underscore constant and hitting shift enter will tell us that this is not an n-dimensional array. This is in fact a data frame, a pandas data frame. So how do we get a n-dimensional array, an ND array, from a data frame? Pandas fortunately has a solution for us. All we have to do is call the values attribute. So all we have to do is put a dot after it and use the values attribute. This retrieves an n-dimensional array from our data frame. And just to prove that it works, I'm going to hit shift enter and print out the value 1.7. 1.7 is the variance inflation factor for our crime feature. Nice. But how do we calculate the variance inflation factors for all the other features? To do that, we're going to use a loop. We will need to loop across all the columns in the data frame. But suppose you don't know how many columns there are in your data frame. So as a challenge, can you output the number of columns in x underscore include underscore constant? Bonus points if you can do it in 2 ways. I'll give you a few seconds to pause the video. Ready? Here's the solution. The first way you can find out how many columns there are in the data frame are using the length function. And you would use the length function on the index of columns. So as an argument, you would pass in the data frame and then put a dot after it and write columns. And this will give you the number 14. The second way you can do this is by using the shape attribute. So writing the name of the data frame and using dot shape will give you the number of rows and the number of columns. So there's 404 rows and 14 columns. To access the number of columns directly, you use the square brackets and then a 1 to return the second element from the shape attributes tuple. There we go. So both of these lines of Python code work as a way of retrieving the number of columns in a data frame. Now, we said we have to write a loop, right? So as a second challenge, can you write a for loop that prints out all the variance inflation factors on all the features? I'll give you a few seconds to pause the video and try this out. Ready? Here's the solution. You write for I in range, and the range would be the number of columns in the data frame. So I could have x underscore include underscore constant dot shape and then 1 and then colon, and then in the body of my for loop I have a print statement with a function call to variance inflation factor. So variance inflation underscore factor parentheses, and then my first argument is going to be, as before, x underscore include underscore constant dot values comma exarg underscore index idx equals, and then what? Now I supply the iterator of the loop, and that's I. There we go. That's it. That's the solution. So when the loop finishes, we can print all done. Let's run it, see what we get. Ta-da! These are all the variance inflation factors calculated for every single feature in our data frame. Now, printing all this stuff out is very well and good. But what if we wanted to store it in a list? What if we wanted to store all these things in a variable? So I'm going to copy the code I have above, come down here, add a few more cells, paste it in, delete my challenge comment, delete this print statement, and then I'm going to create an empty list here, VIF equals square brackets. I'm going to put a comment here. This is an empty list. And then inside my list, I'm going to use the append method. So VIF dot append, and what will it append? It will append the variance inflation factor that is calculated as part of the loop. And when we're all done, we can print our variance inflation factor list. Let's see what we get. So that worked really well. We get all the same results printed out as before, except now we're storing them in a variable. But I'll tell you what, I'm going to show you a different kind of Python syntax to accomplish the same thing. So I'm going to copy this, I'm going to paste it in here. What I'm going to do now is I'm going to run this loop inside these square brackets. And the way I would do this is I would move this part here, which is the body of the loop, if you think about it. And then afterwards, I will add the code for the loop, namely this part. So I can copy that, paste it in here, and note the square bracket at the end. Then I'm going to delete this part here, and I will split this one line over 2 lines, just hitting enter here. That way you can see a lot better what's going on. Now let me run this just to prove that it works. Here you go. So this is interesting, right? We're used to seeing loops like this, but you could also use this syntax here to run the loop inside the square brackets to populate your list. Now, I don't really like this formatting here, so I'm going to write some code to add a data frame at the end using the dictionary notation again. And this dictionary is going to have quef underscore name, colon, and then the names are going to be from my training data set, x underscore include underscore constant dot columns. So this is going to be my list of names. Then whatever, comma, hit enter to go down to a new line. For my second column in my data frame, I'll have VIF as the column name, and then I'll put the variance inflation factor list that we've calculated using our loop right afterwards. Now let's see what we get. We get something like this. We get the feature names here, and we get the variance inflation factor for each feature next to it. Now there's a lot of numbers after the decimal point with the variance inflation factor. So let's round it. And I'm going to use a rounding function from NumPy, np.around, parentheses, have the variance inflation factor inside for the first argument, and for the second argument, I'm going to put 2 as how many numbers I want after the decimal point. So I want 2 numbers after the decimal point. Then I'll put a closing parentheses here and hit Shift Enter to refresh my cell. And this is what we get. Now the variance inflation factors are a lot easier to read. So how do we interpret this output? Well, similar to how we did things with the p-value, we compare these numbers to a threshold. And for the variance inflation factors, the scientific consensus seems to be that the threshold is around 10, meaning any feature that has a VIF over 10 would be considered problematic and would need closer inspection. But looking at our list here, we can see that all the numbers are below 10, and this suggests that we don't have to worry about multicollinearity. Now, some academics are a little bit more conservative regarding their threshold, and they think that a cutoff of 5 is better. But given the fact that our results for the coefficients make a lot of sense, and we are below the threshold of 10 for the variance inflation factor, I'm really not too worried about having a multicollinearity problem. Now, as I've discussed earlier, this housing dataset actually came from a research paper where 2 academics were looking for the demand for clean air in Boston. They were trying to put a value to how much people are willing to pay to live somewhere with good air quality. And I was curious if these two academics tested for multicollinearity as well, and if they mention it in their paper. And what I found was that they indeed discussed this problem in the article's footnotes. The problem that the researchers faced was a little different from us, because the researchers were actually trying to estimate the value of having clean air, and what they had was more than one measure of pollution. For us, in our dataset, we have one variable, NOx, which measures nitric oxide. But originally, this wasn't the only pollution factor that was tested in this research paper. They actually had two different pollution measures, and what they found was they actually had a multicollinearity problem when they included both of them. In other words, one of the pollution features was redundant, and they ended up removing it from their regression model. So I think this is actually quite an interesting solution to the problem if you're encountering it in your own research. Removing an unnecessary feature is a perfectly valid way to modify the model, and it's something we're going to look at in the next lesson. Because in the next lesson, we're going to be making small tweaks to our regression model and try and simplify it. And at the same time, we get a chance to check for that final symptom of multicollinearity, namely seeing if our coefficient estimates change dramatically when we tweak the model. Now, it's getting late over here, and I really need to get another coffee. But I've had so much coffee already, so I think I'm going to have to maybe dilute my coffee with decaf. That should work, right? Anyhow, I'll see you in the next lesson.